This is a big overview of gases from Chem 1, or Honors Chem. Again, big thing with gases is looking at pressure, because pressure has the ability to do work. So anytime we have changes in pressures, we have to evaluate the properties of gases. So again, pressure is force exerted on an area. This is really by the collision of molecules. So the unit is the Pascal, which is PA, which is 1 Newton per meter squared. So again, Newton is the force, area is meters squared. Standard atmosphere is the average atmospheric pressure at sea level and 0 degrees Celsius. Was named after Torricelli, who invented the barometer, and is equivalent to 1 millimeter of mercury. Remember, original barometers worked on a column of mercury, so it's where its rising and falling was measured in millimeters. And bar is used in meteorology, but it is becoming more common in chemistry. So relationships between units, the 1 ATM is 1.325 and 764, and then 1 bar is 1 times 10 to the second kilopascal. So that kilo is the same as any other metric unit. If you look here on your AP exam, there are units given for pressure, volume, temperature. So all of these things are used, and your gas constant is down here to use all of them in joules, liter atmospheres, liter torrs, and then you have that relationship. So kPa doesn't make the AP exam, so you won't be seeing that one. Again, some of your units here are listed on your note sheet as well. Kelvin being in degrees Celsius plus 273. That is given as well on your equation sheet. And your moles of gas, and STP is your standard temperature and pressure. Again, 1 ATM, 0 degrees Celsius. Very important definition. Another standard molar volume is also one that is defined at STP. 1 mole is 22.4 liters. And then you have all of your individual gas laws. So Boyle's law. And you should be able to recognize the graph for this pressure volume. Charles' law uses a direct relationship is going to be linear, as well as Montez Law and Vector's law. So the direct proportions are straight lines. It's just this Boyle's law when it's not. We can make it a straight line by making it 1 over V. So V pressure here, and 1 over volume. Then you can get a straight line for that as well. And then the ideal gas law puts them all together. So again, that combines this first 4 all together with 1 ideal gas constant. You can also have what we call a combined gas law, which is any of these conditions. And again, key is 2 different conditions of the same gas sample. And those are given on the exam sheet. So if you want to highlight those, you figure out what isn't given on the exam sheet. So that's kind of the backwards. They give you PV equals nRT. Okay. So, an R can always cancel out, so you can rearrange it PV over NT equals R. And then just cover up whichever one you don't need. So if I don't need pressure, it can be volumes proportional to temperature, or volumes proportional to moles. If volume is constant, pressure is directly proportional to temperature, and sample size is the same, and then you get your pressure times volume. So very easy to derive those from what's given. Okay, really important, temperature always has to be converted to Kelvin, and that is so T is never 0. Again, that's so you don't ever have division by 0. Never happens because of the Kelvin. Okay, I'm just gonna, instead of trying to type these or write these out for you, it's gonna be much easier for you just to write down the answers. So I'm just gonna give them to you orally. If you need to pause and rewind, it's fine. I'm just not gonna take the time to type them out or try to write them out. So for number 3, if you remember from the ideal gas law, from kinetic molecular theory, gas molecules are constantly moving, as are all molecules. So it's a little more important. So they collide with the walls of the container, and that is what gives the molecules their pressure. So again, collision with the walls of the container. So if we try to explain the laws in terms of kinetic molecular theory, it makes sense. As volume decreases, the particles are going to have less space to travel, so that means they are going to collide with the walls of the container more frequently. So as volume decreases, pressure increases. If we turn it around, if we make the volume bigger, the molecules are going to have to travel a larger distance before they collide with the walls of the container, and that will give you a smaller pressure because there's just less collisions. For number 5, why are liquids and solids compressible? There's just not very much space in between the molecules, so there's no room to force them closer together because of something called intermolecular forces, which we haven't gotten to yet. There's repulsion of the electron clouds of elements when they're beside each other. So in the liquid and solid state, they're as close as they can get without that repulsion being a problem. And then for number 6, if we're explaining Montez Law, so that was the one that Scalar says your book uses a Montez Law. So there's some discussion of who should get credit for that. But the idea is the faster the particles are moving at higher temperatures, they're going to move faster. So if they collide with the walls of the container, they are going to have more force. So just think of it as a car collision. If your car is moving faster, it has more force, there's more impact. Same with gases hitting the walls of their container. And then finally, for number 7, why does increasing the amount of particles at constant pressure increase the volume? So if the pressure has to be the same, more particles would give you a higher pressure because there will be more collisions. So in order to have the collision number stay the same, they have to have a bigger area to work through so that even if there's more particles, they hit the walls proportionally the same amounts because they have to travel a larger distance. So that's just a quick review of some of the basic laws of gases.